Hello and welcome to Physics Platter. In Physics Platter, we are discussing about gravitation. So far, we have talked about Newton's 3 laws of gravitation, Kepler's 3 laws about the rotation of the planets around the sun, right? Okay, the Newton's laws of gravitation says that every two masses attract each other with a force which is called the gravitational force, of course, and that force is given as F equals to G m by r square. Alright, where G is the gravitational constant and the value is G equals to 6.7 into 10 to the power minus 11 Newton meter square per kg square. Alright, M and M are capital M and the small m's are the two masses, and the r is the distance between the two masses. Alright, according to this theory, every two masses attract each other. That means this pen is also attracting me and I am also attracting this pen. Then the question is, why doesn't this pen come to me, or why don't I go to the pen, right? Whereas when the earth is attracting me, I'm sitting here because of the gravity, my weight, which is a gravitational force due to the earth, right? Let's say the mass of this pen is 50 grams and mass of me is, let's say, 70 kg. So the force between the pen and me would be F equals to G mm. So G is 6.7 into 10 to the power minus 11 into mass of me, which is 70 kg, into mass of the pen, which is 50 grams, let's say. So 50 into 10 to the power minus 3 kg, okay, divided by 6 divided by the r square, which is the distance between us. Let's say the distance between me and the pen is half a meter, so 0.5 meters. So 0.5 into 0.5 meters, so 0.5 into 0.5. okay, so what is this value? Look at this. If I write the tens together, then it becomes 6.7 into 70 into 50 divided by 0.5 is 0.25 into 10 to the power 11 plus 3, which is 14. All right, so whatever the value is should be multiplied with 10, so should be divided by 10 to the power 14, right, which is approximately would be equals to something around 0.00000, more or less 10 zeros and some number. All right, so this number is and this is a Newton, of course, is a force. This number is a very, very small number. That means the force between me and the pen is very little, very small force. Okay, that's why we can simply consider this force as zero. We can simply ignore that force, and that's what we do. That's why we don't come to each other, or we don't fall on each other. All right. Now the question is, okay, that's fine for the pen and me, or the smaller masses, but according to Kepler, the planets are moving around the sun in an elliptical path with the sun and at one of its foci, and it is revolving around the sun with some velocity, with a variable velocity, and the distance is also variable because it's an elliptical path, right? Question is, why doesn't the sun and earth, let's say this earth, fall on each other? Because they're also attracting. Of course, there is a huge amount of force of attraction or gravitational force between them, because the masses of sun and the earth is not the small like the pen and me, right? So this force is a huge force, but why don't they fall? Kepler could not explain this. Remember that Kepler could not explain this. It was Newton who actually explained this. Whenever something is rotating in a circular path, or rather in a curved path, whenever a mass moves in a curved path with some velocity, the velocity always acts along the tangent, okay, along the tangent of the circle at that point, and there is always a force acting away from the center of the circle. All right, and that force is called the centrifugal force. That force which is away from the center is called the centrifugal force, and this is the force due to which whenever we are sitting in a car or in a bike, or let's say in a train, when the train or the vehicle is turning in a curve, we feel a force outward. Okay, and this is the force, centrifugal force. Now whenever there is a force outward, when the body is already moving in a circular path, that force must be balanced with something, and that force must act towards the center of the circle, and that force, which is exactly equal to the centrifugal force and acting along the center towards the center of the circle, is called the centripetal force. Alright, the centrifugal force is given as F equals to mv square by r, where v is the velocity or tangential velocity of the body, m is the mass of the body, and r is the radius of the circular path or radius of the curvature. Alright, now earth is also moving along a circular path, if we consider it basically curved path, right? So there is also a centrifugal force acting on earth as well, and that's because, and that is the force that actually keeps earth from falling to the sun, all right, due to the gravitational force. All right, so this force, centripetal force, equals to the centrifugal force when the body is rotating in a circular path or in a curvature, in a curved path. All right, okay, now the question is, let's say Newton said, according to Newton's gravitational force, F equals to g m by r square. All right, we can see very clearly that F is proportional to the mass. If we increase the mass, the force will increase. That's more or less visible. Then F is also proportional to the small mass. That's also visible. F is inversely proportional to the r. That's okay, because if we increase the distance between two masses, the force between them will also decrease, right? But then why square? Where did Newton come? Where did he get this idea of the square here? Okay. Alright, this actually came from this centrifugal force. Alright, because he said that this gravitational pull is balanced by the centrifugal force. That means if we calculate this centrifugal force, we already know the gravitational pull by the earth, by the sun. Alright, so to do that, let's say the body is moving. Let's say a mass of m is moving along a center in a circular path with a velocity v, of course, and radius small r. Alright, so what is the perimeter of the circle? 2 pi r. Alright, and let's say the time period of rotation is capital T. The time period of the rotation of this body is capital T. That means if the body starts from A, it rotates all the way and comes back to A again at time t. Okay, so what do we get? The velocity equals to the distance by, or the displacement by distance traveled in 1 second, right? So here the particle moves 2 pi r distance in t seconds, so there should be the velocity equals to 2 pi r by t. All right, if we square both the sides, we get v square equals to 4 pi square r square divided by t square. All right, now the centrifugal force on the particle is given as mv square by r, right, equals to mv square is this one, which is 4 pi square r square divided by r into t square. All right, now if we multiply both numerator and denominator by r, what do we get here? We get equals to the centrifugal force F equals to 4 pi square m. In the numerator we get r cube divided by t square into 1 by r square. Am I clear? Alright, I have just reshuffled the term and written it like this. Okay, now look at this term, r cube by t square. If you remember Kepler's third law, that says the cube of the mean distance of Earth or mean distance of a planet from the sun is directly proportional to the square of the time period, which gives us r cube divided by t square equals to a constant, right? That means this is the constant term. Now this 4 pi square m, this is also constant. 4 is a constant, pi is a constant, and mass is of course a constant. That means this whole term is a constant, right? So we can say this constant as k into 1 by r square. Now F equals to constant into 1 by r square, which gives, and this is the centrifugal force, mind it, okay. That means we can say that the centrifugal force is proportional to the 1 by r square. That means this force is inversely proportional to the square of the distance between them, right? So this is where he came up with the idea that the gravitational force is also directly proportional, inversely proportional to the square of the distance between the two masses, because the particle which, or the earth, the planets which are moving around the sun, they are not going or moving towards sun, they are rotating all the time. That means the centrifugal force which is outward is balanced by the centripetal force which is inward. That means if you calculate the centrifugal force here, we are already done with the centripetal force, right, at an instant, right? So this is where he found the idea of the inverse square law. Inverse square law, which is the force between two masses is inversely proportional to the square of the distance between the particles. All right. Okay, so that's all for today's class. I hope you have understood what we have done today. In the next class, we will probably finish up with the rest of the part of the gravitation chapter. So that's all for today's class, and see you in the next class. Till then, take care.